Thank you for watching Knowledge Academy. In this video, we'll be talking about motion in 2 dimension or motion in 3 dimension. Okay. Before we start talking about motion in 1 dimension, 2 dimension, or 3 dimension, we know that motion is more relatively associated to a term called displacement. And displacement could be 1D, 2D, or 3D. So displacement is a motion in a straight line. Okay. Now, when you're talking about motion in 2 dimension or 3 dimension, we have to use a term called vector. And those vector is basically telling the position of object in particular location. What does that mean? It means if I have an object, let's suppose A, and is moving along this line or this curve, and is reaching out to another or passing another point called B. I want the two position. What I'm going to do, I'm going to say, well, where is my location? It's here. Let's suppose O. I'm going to make two vectors. And I'm going to call RB, RA. What is RA and RB? Those are RA is a position vector. And if you want the delta between the two, which is I'm going to be drawing it with the color, maybe green, I'm going to call it delta R. Really, what this delta R is, I can say that is position vector RA. I can also say it's position vector R. These are the two position vector. And if I want the delta R or delta R, I can say it's RB minus. Now, let's step back further and moving and talking about what this position vector is. So really that RA is a point A. So a point is in space, and this point have 3 coordinate. This is x, y, z coordinate. This point have x, y, z components. So what they're gonna do here, if I want to do RA, my R is going to be like this. And I can also define this RA with these three vectors and their complement. For example, let me just change the color. So the white color vectors are the complement of this R. This is RA Y. This is R X, and this is R A. So maybe I can write this R vector or RA vector called X component I plus Y component J plus Z component. These I, J, K are the unit vector in big fraction. We discussed them in the previous lectures. So this is my position standard form. Okay. Now, if I want the position vector at a particular point, I should give you coordinates, so maybe 3, 2, 5, or minus 3 to 5. What you can do, you just substitute the value. So R at A, position vector R at A equals to minus 3 meter I plus 2 meter J plus 5 meter. Okay. Note that the vector, note that RA is drawn from origin 4, 0, 0. So this vector starting from this point, this is considered the origin where everything is from 0. If it's not 0, then you have to take account the difference between the coordinates. So they say 3 minus 2, whatever is the coordinate of this origin vector, you have to minus that. Okay. Now, if you have a position like this and you want to get the delta, so what you're going to do, you're going to take delta R equal to R2 minus R1 or RB minus R1, And if you want to substitute the value, you can directly just substitute the value. So the true coordinate of x1 and x2, or r1 and r2, substituting like this, so this is x2 minus x1. So really these are the two points. X1 and x2 are the point of this. So this is x1 y1 and x2 y2. And these are the value I'm substituting here. I then plus y2 minus yj plus t. Yep, I can write this thing in another form. Right, like it goes delta x plus delta yj plus delta z. Yep, we're going to talk about problems. So let's discuss a problem for a vector. Talk these terms. How we're going to substitute the values that can explain. Now, since this is a calculus based one-dimensional, two-dimensional, three-dimensional motion, so my dimension is given in the form of time. So it's given in the form of equation. For example, x is given 0.25 t squared plus 1.59 plus t. Same thing with y. So you can see here is given some equation. So this is called equation. And in order to find the equation and then velocity, what you're going to be doing, you need to remember, we just take the dx of t. So really we take this equation and take the derivative with respect to x. Now let's take a problem and take a look into that, and then that's going to help us to explain. Let's take a look at another problem. Is an object moves in x5 coordinate and its xy components, x and y components, both change as a function of time. According to this equation, x is given something, y which is 0.2 squared minus 1 plus. These are the two equations are given. Let's talk about A, what we need to find out. What is the position vector R in the unit vector form? In unit vector form at t, time is 15 seconds. Okay, that's the part A. And the part B is, what is the position in magnitude and angle form? In magnitude and angle form. Okay, so we have two parts. Actually discovered both sides of this kind of problems. So you can see here. So what we're going to do, we're going to write those equations and substitute the value. So we're going to finding x. The solution is we're going to take the x and substitute the value 0.3313, so 0.31 minus 0.31, and then t square. So t is my 15 square because this is given in 15 seconds. So I'm going to substitute wherever the t is, I'm going to be substituting the value, and it's going to be 15 plus 20. We solve this, it's going to be 66. Right? Same thing, I substitute the value in y, it's going to be 0.22 power 15 minus 9.1 and 15 plus 20. And if I solve this one, I'm going to get minus 55. So minus 57. Yeah. So this is x and y, and we just discussed about that. R equals to xi plus yj. So I'm going to substitute the value here. So R is going to be like 6 meter minus 57. Basically, this is an answer for part A. In part B, I need to find out in magnitude and angle formula. So really, I need a R in some numbers and R angle. So really, let's suppose whenever the R, the total position vector is given, I need to find out the R vector in a number, and I also need the angle. Okay. So part B, what you're going to do, we're just going to do part A is pretty straightforward. A part B, I'm going to be saying R equal to Rx squared plus or x squared y squared. You can call it here as x and y. So you can call x squared y squared in your situation. So maybe you can write better squared plus y squared. And if I substitute the values, 66 solve them, 6 squared plus minus 57 squared is going to be 7. Okay. Now we know the theta equals to tan inverse y x, and I'm going to substitute the value tangent inverse y would be minus 57 x would be 66 minus. So really this is the part D answer. We're gonna part this guy. Okay. Now, since we understand all these kind of position vector and how we're going to substitute the value in the position vector, let's talk about velocity. Because our goal is to moving into all the motion content of position vector, velocity, then acceleration. Okay. Let's take a look at another problem. Now we're going to be talking about average velocity. In average velocity, you're going to take the velocity equals to distance over time. So since we don't have a distance here, we really have a position vector. So I can change this term for delta x or delta r. Delta r have three components: delta x plus delta yj plus delta z divided by delta. We can also write like this: v average. And by the average means actually we have 2 points. We're going to take the average between the two. So delta r or delta. Okay. So let's suppose if I have a given a vector, for example, a particle with displacement and the vector is given 12 meter j plus just to I and j, and maybe I and j, just leave it there. And what you're going to do, you just this is a given, and then it move from in 2 seconds. 2 seconds. So what is the average velocity? The average velocity here is delta r over delta r is 12 meter I plus 3 meter j divided by 2. So it's going to be just divided into 6 meter I plus 1.5 meter j meter per second. That is my average velocity. That is my average velocity. Okay. We can also write this from like velocity. So we can see it's Vx. Just like this, I can say it's Vx equal to delta x or delta t Vy equals to y delta t, and Vc c. We can have these 3 components. We can separate them and write like this. Okay. Now, if you want to talk about this, let's take a look at an example. Okay. Let's take a look at another problem. An example 4.1. To give this example, we had position changing as a function of time. We had position changing as a function of time. And what is the position changing as a function of time? X equals to minus 0.31 t squared plus 7.22 plus 28, and y change position is changing 0.22 t squared minus 9.1 t plus. Need to find out a, what is the position, what is the velocity vector? What is the velocity vector v of the object at time equals to 15 seconds. So you notice it's pretty much the same problem. The only difference is that they're asking you velocity vector. Over there, you're asking position vector. B. Now, same thing. Now express this velocity vector in magnitude and angle phi. We have two parts, straightforward. The only difference is that we learned this is x is given here, right? This is the x, and we know the velocity equals to dx over dt. So that explains everything. I just want to take this x and then take the derivative with respect to time. Same thing y. I'm going to take that derivative with respect to y, but I'm going to call this vx, and when I take the derivative with respect to y, I'm going to call it vy. So dy over d, dx over dt, dy over dt. Yeah, the two components. So what I'm going to do, I'm going to just start jumping into that and start solving it. So vx equal to d over dt, and then here I'm going to be calling x, so is equals to d over dt, and then x is given 0.31 t squared plus 7.2 t plus 28. And if I take the derivative, it's going to be minus 0.62 times, you're going to multiply by this, and then t to the power 1, which we just writing t, and plus 7.2 because this t will be eliminating, and then 28 completely gone because it's going to be constant derivative is 0. So we got this. Vy, on the other hand, is going to be pretty much same story. D over dt. Now we'll be writing 2 t squared minus 9.1 t plus. Yeah. And if I take the derivative, it's going to look like 0.44 t minus 9. Yeah. Just like vx, we got vy. Now we got pretty much everything, so I'm going to write in here my velocity vector. Velocity vector equals to minus, and I'm going to substitute the value here. So if I substitute the value, this will become, I'm going to just substitute the value at time equals to 15 seconds. So what I'm going to do, I'm going to say is here 0.6162 15 plus 7.2. Here I'm going to say the same thing. I'm going to take this value for Vy and then substitute the time 15 seconds. So it's going to be minus 9.1. If you substitute the value, this one's supposed to be come out minus 2.1 meter per second, and this one comes out minus 2.5. Okay, so I can write my velocity vector in a which form? In a velocity vector in object in a unit vector form. So velocity vector I can write vxi plus vyj, and I can substitute the value. So v equals to minus 2.1 meter per second I plus, I'm going to associate the value j. That is really my velocity vector. Now the part B, I have to do a little bit more work here. And in this part, all I have to do, I just take the velocity and then find the velocity, magnitude, and angle. So magnitude velocity equals to vx squared plus vy. And I'm going to substitute the value minus 2.5, so 2.1. Both are in a minus sign. If you solve them, you're going to get 3.3 meter per second. Okay. We also know tangent theta equals to Vy over x. From here, I can write theta equals to tan inverse. My Vy is minus 2.5, 2.1 with minus sign, minus gonna get cancelled. Divide them, you're gonna get tan inverse 1.19. And if you take the angle, you take the tan inverse, is gonna be 130 degrees with minus sign. So you know minus sign means the velocity is supposed to be here somewhere. Somewhere here maybe. And this minus sign is saying that we technically measuring from negative x-axis. We're supposed to be measured from positive x-axis. So what you're gonna do? You're gonna take this minus 130 and say theta equals to 180 minus 130, and it becomes 50 degrees. So really, this is 50 degrees now. And this is my vector. So in this vector, this is my angle, and that is my magnitude. In the same way, we can write acceleration. If I'm asking the acceleration, nothing but I can write acceleration vector like this, just like velocity and position. You can call axi plus ayj plus az. I can also write a equals to, or ax equals to vx over t, ay equals to vy over delta t. And also az equals to delta vc over delta t. Yep. And same, pretty much all the applications apply on that. So if I want to be adding the acceleration, I can add those components. Let's talk about the projectile motion. Okay, let's talk about a projectile motion. Projectile. Okay. Projectile motion means just like a projectile, we throw something with an angle. Okay. So first thing first, before you start, if somebody throwing an object like in a straight line, you can call velocity. Maybe you can call vx. If somebody's throwing this object, vertically up, you can call it v, or maybe you can call it y. So these two cases pretty straightforward. But if someone throwing an object like an angle, right? Now this object actually is not going to go straight. It's going to be making this trajectory. And this trajectory actually called projectile motion. So in order to start this one, let's simplify. If you're throwing an object with an angle, basically it has a v component, velocity component, vx component, and also a vy component. You can calculate vx equals to v cos 30 or theta, whatever theta is, and vy equals to v sine 30. These are the two. If I want to draw this thing here, I can draw it. But before than that, I have to apply the motion equation of motion, like Bf equals to Bi plus At, or I can call it equation of motion. 2As equals to Bf square minus Bi square, and S equals to Bit plus half. These are the three basic equations. Okay, I need to apply this equation in x form, in x motion, and also in y motion. How? I can just write here just like that. So I'm going to take equation number 1, 2, 3 and convert them in x and y form. So the equation number 1, Bf, or usually in this book we don't call f, we just says v, is going to be with x. So everything you just write is going to come with x. However, time doesn't come with x because this object is going to leave here and arrive here at the same time. Yeah, so time will be same for both. How can I write the first equation in y form? Vfy plus v equals to viy plus ay. Acceleration along y-axis, you can call them ay, or you can call them g, because we know when some things are dropped, we use g, called acceleration due to gravity. So when things are going vertical direction, acceleration due to gravity. So in particular, those cases, I can rid of this a by to g. Same thing, I'm going to write the second equation, 2a delta x equals to bf square minus bi square plus bi x, and then x delta x equals to vi x t plus half ax t square. Same thing here, 2a delta x equals to bf y square minus bi y square. Delta y equals to b I y plus half g. I can call g, I can also call this one as g, I can also call this one g. Wherever the a is, I can call it g with minus sign. Right? So everything will be minus, minus, minus. And then t squared. Now I can draw projectile motion a little bit better for me. So what I'm going to do, I'm going to be just, I already wrote these equations. I can maybe eliminate or erase this guy. So we can draw here maybe. But so I'm going to draw here maybe, and it's going to throw the object here. It's going to go and land here. When it's going to be land, I can draw this thing. I can call this v x, call this motion vy, and this motion I can call v naught. So vx equals to v naught cos theta. Theta is this angle. Vy can be written like this, v naught. Like that. Yeah. While this object is going into different spot, two kind of acceleration apply on this. One is g, acceleration due to gravity, and g is constant. Okay. And now ay equals to minus g. So when you apply the motion, when you apply the equation of motion of this one, all the a is replaced by this minus g, right? and all the x is going to stay x. All the x is going to stay in x. So we can write those. Now I can write these little arrows over there. So if I take any point like this point, in this point we have two velocities. The one velocity is called v x v, and this one what called v. And there's a vy here. Then this point, what's going to happen? This object is going to go here. This object is going to go, stop, and then come down. So really, the object is going to just like going, slow down, stop, and then come down and come down fast. So really, at this point, vy equals to 0, but vx not equal to 0. Vx have a vy does not. So remember, two velocities were acting on this object. One is carrying him forward, one is carrying him upward. The one which is carrying him forward is constant. So Vx is constant. Vy does not constant. Vy is actually changing from here. Slow down as going up is going to be slowed down is at almost 0, then start coming fast when it's increasing when it's going down. Okay. So right y is 0 here. Then you're going down. I have Vy and so Vx. Same thing, every point is going to be coming down faster and faster. So you can apply those equations onto this particular point. Okay. Now let's take a look at some problems so we can understand this topic a little better. Let's take a look at another problem. This problem is position vector problem. We'll be asking solution. A position vector of electron is this. Position vector is given R is given by I minus 2 plus 2k is our unit vector. Find the magnitude of R. So we need to calculate R. R equals to 5 squared minus 3 squared plus 2 squared. And if you add them together, it's 6.2. Take 50 squared is 6. Part B saying is sketch the vector on the right-handed coordinate system. Right-handed coordinate system. So if you learn in the book, you notice one. Sometimes they say this is x, this is y. Sometimes they say this is y, this is x. So right-handed coordinate system, if the person is standing like this, their right hand is x, and left hand. So what I'm going to do, I'm going to just move and apply. So I'm going to get this, and I'm going to say this is x, this is y, this is called right hand. Now here I'm going to be drawing this vector R. So vector R is here. This is x component. This is x component. This is y. This is c. So x component is 5. Y component is minus 3. So c is 1. So that is and c is 2. So c is 1. Okay. 1. I'm going to make a line here. Now I'm going to draw the vector. That is my vector. Okay. I want to adding all these numbers. This is 5. The back side, the yellow red line is and these two sides. I can draw this vector. Remember, these are the components. Let's take a look at another problem. Okay, this problem is a little bit tricky, so let's read this problem together. A train is at a constant 60 km per hour moving east. So this is east, north, south, west. So this train is moving towards east and then going to certain angle here, and then is going to be on the west. So let's draw this. What it says. This problem is saying plane is moving east. This train is moving towards this way, right? And how long? 40 minutes. Then it's going to make the angle from 50 degree east to north. 50 degree east to north means basically making the angle from here. So this angle is 50, so this angle is 40. And how long is going to be running here? 50 minutes. And then it's going to go towards the west. And how long is going to be running? 50. Okay. So first thing first, we're going to say is delta R 1. Maybe I can put 1 or 2 or these are the kind of, but I need the position. I need position vector. So I'm going to call R1 is equals to 60 kilometers per hour. So I need to convert it to minute per hour. So I'm going to call it 60 minutes per hour. And this train is running for 40 minutes. So I think this minute and this minute is cancel. This hour and this hour is going to be cancelled, and left over is kilometers. This hour and this hour is going to be cancelled. This minute and this minute will be cancelled. And the answer would be 40 kilometers. Which way? You're going towards east. So I'm going to go right. In the same way, R2 does not have one. R2 is just like this way. So it should have one component here, R2x, and then one component here, R2. Okay. So I'm going to do the R2. Now R2 equals to 20 kilometer, and then cos 40, cos theta. So the theta here is 40. So I'm going to say sec 30, 40i plus 20 kilometer. Okay. Now I can just solve a little bit so I can get the numbers. So I'm going to solve this maybe from 15.3 kilometer I plus 12.9 kilometer, and that is my result. Now R3 is going to be straightforward, just like R1. The only thing is the difference because going towards the negative direction. So I'm going to go minus and say 60. That's the velocity, kilometer per hour is given. I'm going to convert it into meter per hour or minute per hour. Sorry. So I'm going to say 60 minute per hour, and then how long it's running? 50 minutes is running 50 minutes. So this can be canceling a lot of things. This, and then minute is going to be staying there. Okay. Now if I solve this, is going to be answer would be minus 50. The 60 definitely canceling out here. 60 minus 50 kilometer in watt. is going to be I, because along x-axis, right? Anything along x-axis will be I. Anything along j-axis, okay, and y-axis along j. So I got all three numbers. So I'm going to just simply substitute the values. Delta R equals to delta R1 plus delta R2 plus I'm going to substitute all the values here. R1 is 40 kilometer I plus 15.3 kilometer J. Oh, that's I here. This means this I plus 12.9 J and then minus 50 I. Okay, everything is in kilometers. We don't have to write again and again. Just for save some space, I'm going to just don't write kilometers this time. But if I solve this, going to be answer this. It's 5.30 I plus 12. Now we need to find out delta t. Delta t is total time is 40 minutes and plus 20 minutes plus 50 minutes is 110. Right, so it's going to take 40 minutes here, 50 minutes, 20 minutes here, 60 and 60, 50, 110, 110 minutes. I need to calculate the average velocity. Average velocity is delta R over delta. So I know everything. I'm going to say is 5.3 kilometer I plus 12.9 J minutes. Right? I can take this since this is in kilometers, so I have to convert it to kilometers. What I'm going to do, take this and divide it by 60, so I can get in kilometers. So 110 divided by 60, and the answer is 1.8 hours. So I can maybe write 8 hours. Solve this thing is going to get something, right? Get something, and is basically is a vector, so it's going to be 2 kilometer per hour, and it's going to be I plus 7.01 kilometer per hour J. Right? If I want the magnitude of this average, I can basically call average and write like the square root and says 2.9 squared plus 7.01 squared. We solve this thing. It's going to be called V average velocity equals to 7.59 kilometer per hour. That is the answer for this problem. Let's take a look at another problem. In this problem, we have a car propelled in XY plane. Acceleration component is AX is given and AY is given. It is initial velocity has a component of this and VY is this. In a unit vector notation, what is the velocity of the car when it reaches to a greatest Y coordinate? Okay. When it says greatest Y coordinate means it's basically it's going to be 0, right? So I'm going to apply the equation. So it says V y equal to 0, characterizing y equals to y max. And what does that mean? It means if somebody is throwing a projectile here, it's going to go. When it go to the reach, this y distance by a max, right? This y is a y max. When y is y max, what is the velocity of this? We already talked about vy should be equal to 0. And here, this is exactly what I just did. Vy equal to 0. So I'm going to substitute the equation. Y equals to I'm going to equation I'm going to be using v f equals to vi plus a. This is what I'm going to be using. Okay. So I'm going to substitute this value, and it's going to be 12 meter per second plus minus 12 because negative direction. So 2.12, 2.0, and then meter per second square is given in the problem, and then t. From here, I can substitute everything, whatever I have it, and I can find t, and then t equals to 6 seconds. Now I need to find out the velocity of x. Vx equals same equation, Vx equals to Vi plus a t. So I'm going to say Vx equal to Vi. Vfx equal to Vfi plus at. That's better equation written in the written form. So I'm going to say is Vx equals to 8 is given plus 4 is given, and then t squared, t is given, t we already calculated, 6. So when you solve this thing, is going to be Vx equals to 32 meter per second. I say, so really the thing is, if I want to do the velocity of the card here, so let me just draw here. When card reach out here, card have two velocity here. This velocity, this component, this component. Card go here, it has a little bit less velocity here, and then big velocity. This is a little bit small velocity. And card gonna go further here. This, you see, this component is getting smaller, 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 and basically here has become 0. So at this point, only which one is left? Vx. Okay, this point is Vx left. So if I'm going to be drawing another way, I'm going to be writing v velocity equals to Vx squared plus Vy squared. At where? At this point. Maybe I can call this point B. So I'm going to call velocity at point B is a square root of these two. So this guy is already 0. So everything is this. This square root is square and square root getting cancelling out. So really, velocity at B equals to Vx only. So therefore, the velocity of the car at B or at Y max position equal to what? 32 meter per second. In which direction? It should be I. See, because it's going this way, so it should be I. Thank you for watching Knowledge Academy. Please subscribe my channel.